Den var en sikkert translation ingenting.
Alright. So we have like a few minutes left.
10x, så han har pluss 0. Men han har 18 altså. Uten arm.
Thanks. So we just wrap up with a few concepts and hopefully a bit closer to OpenGL, so we can actually put it to practical use quite immediately, in fact. So one of the challenges with textures was, again, we dealing with raster-based, outputs, right? Our viewpad is raster-based. We don't have vector-based output that we're dealing with, at least. So, and the issues is there, especially if we're dealing with 3D space, that we have effects of, proximity and distance. We have the z-axis basically, and that thing is a bit annoying. Because it causes us trouble, and we'll see how that is the case. But before we move to the z-axis, even on the x and y axes, we have a similar issue. And the question is simply there, what happens if we have a texture that's not large enough to capture, or is simply not attached to the edges of your viewport, meaning it doesn't cover the entire screen, if you like, right? So, and the question, OpenGL allows a set of parameters to control that. So the idea is basically, all right, if I have an image, but my actual window is considerably larger, and I don't want to stretch the image, but I have the u and v coordinates fixed to particular coordinates in the two-dimensional space here. What happens if the window is basically larger? And there are different properties you could use, either, for example, to repeat the image, so it's repeatedly mapped over the whole window, which is like a bit 90s, I guess, right? So I don't know if you have seen that before, that people easily just simply represent it by repeating it. Or the idea of clamping. Clamping uses the bordering pixels of the image and extends those to the window border. So that can be a reasonable effect. If you, for example, you guys know those 3D canvases, which are kind of in-ish, or were in-ish, no? Like the canvases where you print pictures on, they have like a bit of an offset on wood, something like that. No? Okay, cool. But they do the same thing. They basically do clamping there over the borders. They basically continue the textures that, like the colors that are bordering at that side. So in the syntax to do it, I'll show you more examples, but the syntax to do it is GL text parameter, then you indicate what type of textures you're dealing with. More importantly, if you're interested in the x-axis, or now to make life a bit more complicated, the u dimension of the texture space, which is represented as S here. I forgot what it stands for, I need to look it up. And similar for T, you can indicate, okay, along the x-axis, if you like, you repeat the picture, and along the y-axis, for example, you use the clamping to the border. So you just, have those seams of color going to the borders, basically. And there's, I think, those 4 different approaches. So since we like kitten pictures here, because we're doing IT, and IT is about kittens, those are the possible alternatives. So we have repeating, mirror repeat, clamping to the edge, that's the most horrible one, and then the clamping to the border, it just repeats the bordering color that's outside the original image and fills up the entire window space. Are there any other functions? I think those are the basic 4 ones. If there are more, play with them and see what they do, but you get the essence here. Again, the issue is just, okay, what happens if I have an image and there's simply not enough texture in the available to cover the entire window. Okay, that's quite straightforward one. Another aspect to motivate is the idea of having projections of texture. So not only do you have the obvious texture and you map it to some sort of surface, but then you play with the surface, right? So geometrically shape it, shift it, either in terms of the model itself, or from the viewport perspective, right? So from the basically monitor perspective, plus the viewer's perspective, the camera perspective that you want to take into account. And this can lead to interesting artifacts. The most obvious one is when you, for example, zoom in, you get those ugly corners here, right? So it's a relatively rigid corners you're dealing with, because we're dealing with rasterized systems, so fixed resolution. And there are various strategies of smoothing that out, actually. Do you guys know some of the strategies? Or intuitively, which would be a good one? Yep.
Anti-aliasing.
Yeah, we come to that in a bit later. Yeah, that's cool, but more the advanced. Let's start very simple.
Blur.
Blur, yeah. How do you do blur? That's good.
You just say that neighboring pixels has a little bit of the color of neighboring pixels.
That's right. But so basically, some sort of interpolation, right? So of all the bordering pixels, and that seems to be the way to go. So yes. So the issue is here basically, okay, how do you decide for an undefined pixel what color to actually provide, right? So if you zoom in, for example, and the idea is basically the simplest form that we saw that's just there, which is not a solution, but this causes those artifacts, is to pick the nearest neighbor anyway. So you have a harsh border basically because you pick one of the colors that's closest to the actual coordinate that you're projecting to, because obviously again, if you are changing zooming in or what out in or out or whatever else, then your texture coordinates or raster will be distorted, right? So in this case, yes, you would get rather harsh choices, and as you mentioned, we have the interpolation idea. Why not use all of them and then get some sort of middle value, some average value, weighted average, in fact, because it would consider the relative positioning of the target position in the text space here, right? So you get some kind of brownish, which would smoothen things out and would start causing this kind of blurriness there, right? So this border effect, if you like. Interestingly though, so this is called linear interpolation, right? So we actually have the linear, you use the borders and you think you're sweet and everything is good, and now we have a continuous color scheme and our borders become relatively smooth. But there seems to be another effect if you apply this linear interpolation scheme on further distances. You may get incorrect mappings in when you look at farther distance, and the reason is simply there that you have a disproportionate. You see disproportionately more from a given projection of one pixel than another, right? Because based on the angle of your surface, based on the direction from which you're looking at a given surface, you may actually perceive more of that red pixel as opposed to the other ones. So just doing the linear interpolation may not be the right cut, but actually you need to put more weight onto the color that you have actually perceiving the most. So that's one of the aspects there. So particular further distance, you have this kind of distorted effect then that can happen. And the idea is there that the perspective needs to be taken into account when it's about determining which pixels you actually see, and then use those as a basis for interpolation. So, and that's called anisotropic filtering. So isotropic would be equal consideration of all pixels, anisotropic not equal would be considering your perspective onto a set of pixels and then use that as a basis for interpolation, right? So you have disproportionately more red from the camera perspective, so you put stronger weight on the red when you interpolate the average values, when you calculate the average value. That's one of the aspects. So that's the baseline of doing things. Okay, if we think about zooming out, what's the challenge we have there? Right now I talk more about zooming in, but zooming out is obviously an issue as well. Can you guys imagine another challenge you got suddenly face? So we're zooming in, we get large pixels, we use interpolation of the pixels we see, and now the opposite case.
I don't know what it's called, but I know something. You get an artifact which you use anisotropic filtering to prevent it.
That's one of the aspects.
The lines get
cool.
like blended together, so you things far in the distance gets really ugly.
Yeah, that's right. We get to that again as usual. You're one step ahead. So pedagogically, I want to keep it a bit, you know. But what's, yeah, you know, since you're mentioning it, why not? So, no, what, okay, that's actually this one, what I want to say. That's precisely what you're describing, I think. If not, correct me. But the idea is here, if you apply those filtering schemes in the distance, you actually may have like secondary effects. So suddenly, because you're using the same approximation method, if you like the, you know, filtering mechanism, you suddenly get secondary patterns, so aliases, that are not a reflection of the geometry or, yeah, of the in this case, topology you're representing, but rather an effect of the method itself, right? So you have those weird, you know, strides or weird line striations, as they're referred to in textures, that are actually not so much a result of texture, but only of the way you're actually processing it. So that's another problem. Yes. But what causes that issue to some extent? This is the effect that we see. So yep.
Is it because you're trying to jam something that's actually continuous into a discrete area?
That is, yes, exactly. Yeah, you enforce. Yeah, actually, right. You're enforcing a discrete representation. That's right. Anyway, which we need to do on our raster-based images. But think about. So beautiful. Who can see my 4 pixels here? Everyone? Good. No one needs to go to the eye doctor. It's pretty good. So we see those. But now imagine we are moving out of this room and looking from the far back here, right? So would you be able to distinguish them? Most likely, yes or no? Who thinks? You, yes? You know? I would say no. Anyone else? Okay. So probably no. You guys are in a good position to argue that it may not be a no. You probably may actually be already on that level and actually see the bigger. You probably wouldn't even see the substructures anymore at some stage, right? But you would actually fall back and only see the next level of aggregation. So you would see those here, right, as pixels, whereas you guys are still seeing the inside ones, for example, right? I'm making it up here, so, but you know, with a sufficient perspective, we may be able to buy into the idea. So the idea is that if we interpolate on, let's say, the 4 adjacent pixels that are closest to the texel position that we have based on our projection, we get those artifacts because we're basically operating always in terms of, as you say, we're discretizing based on those fixed pixels. But the idea is that we are not sufficiently taking into account that you actually lose resolution when you look at it from a further distance. So basically, you will no longer see those 4 pixels in the first place because they become too arbitrary, too small if you zoom out. But in fact, you're looking at larger clusters. So you need to have a your pixel. How do you say? You basically the size of the perceived pixel becomes bigger. Yeah. So you would need to interpolate either across all of them, for example, right? So to get the appropriate color representation or not. But if you're not doing that, you get those artifacts. If you stay at the same level of interpolation, look at the same unit of interpolation, you get those artifacts. The idea is there that the further your z-axis moves away from a given object, the more coarse-grained your interpolation needs to be. So you need to look at bigger areas and calculate the interpolation based on those ones. And that's one way of dealing with the issue. However, this becomes quite expensive computationally because it would really mean that you need to identify the areas based on your perspective, then in real time calculate this one. And what would be possible pathways of dealing with this issue? Any idea what you could do to deal with this? There are various strategies. And it's called anti-aliasing, surprise, surprise. You guys are more than aware of this, and that would be a possible outcome effect of it. Any ideas? One of the most common ones, so there are various approaches to it. And one of them that you guys have probably heard about or seen was the idea of MIP mapping. And the idea is there, instead of just having one texture, at compile time you're basically creating a set of minifications of that texture. You basically take various variants in terms of size of that texture that are realistic for a game, but usually it's kind of a linear function there. And the idea is that depending on your projection, you can identify which two images are the closest to the perceived distance or the size that your image actually has based on your model, your z-axis, right? How far you zoom out, you can determine, oh, hang on, it's actually not close to that texture size representation anymore, but actually to this one and somewhere in between those two ones, right? And the idea is then to use those ones for interpolating the actual color for a given object. So the idea is you make it way faster by loading it into the GPU before you actually start rendering. So you always have them cached basically and access them real time, and then operate on those ones as opposed to on the real image, right? Because it's simply faster, and that's called MIP mapping, the idea. This is obviously the case if you have the textures handy. The alternative is to have simply more. Here's another example. The alternative is to use the idea of sampling over larger spaces. So you look at it from a more coarse-grained perspective and then determine the average values across a larger space, and then have a weighted kind of a weighted representation. So if you, for example, cluster all those elements here together as one single pixel, you use the weight of those ones respectively and the ones that are lying outside. So basically using a real-time calculation by taking samples across a larger set of pixels, like coarse-grained areas, and then you determine the color based on that one. So that's the idea. So you get a smoothened out perception even for further distance, assuming that your pixel was originally in, for example, 4 pixels represent one of those blocks here, then you would get a more smoother representation as opposed to operating on the individual pixel level, right, which would afford the harsher kind of artifacts that you see. And here you would interpolate in all the cases where your border, let's say visibility border or whatever else, or border of texture would cross multiple pixels, so texels in fact. So yeah, that would be one way of dealing with it. So you sample across larger spaces. What else do I want to say here? And then you basically, use a weight-based approach, right? So the number of neighbors that actually lie in the darker space based on their corresponding neighbors. For example, the entire area is green, and this one is to 3/4 in the green space, so you put a considerably stronger weight on the green bit, whereas here it's a bit more balanced, so you have more white elements. Here's a softish green, because only 1/4 is actually falls into the space that is captured by the green coordinates. So if you have this border in this area, so that's one of the ideas there. And this creates this softened blur where borders become. Yeah, please.
So the rectangles there in the second picture, those are the average of all the pixels within the
That's right.
rectangle?
That's right. I'm sorry, I should have made. Yeah, that's the average of the bordering coordinates, right? So yes, of the bordering colors basically, right? And then you get a smoothened kind of approximation of the color transition, so you don't have those hard artifacts anymore. And this you can do. So that's a different method. Basically, you can apply that obviously to MIP maps, so the pre-calculated images, but also do it in real time on the actual, coordinates that you're having in your projection. So this is a bit more expensive because you definitely need to do it real time. But that's another way of dealing with this. So basically taking a set of samples. Also, you may not be able to calculate it for all individual pixels, you may not simply not have the computational time. You can optimize it by taking random samples. So the color information of random coordinates in order to determine the target color, right? The target interpolation. So you don't necessarily need to do that comprehensively. So that's one way of dealing with the performance impact that it would otherwise have. So especially if you have larger scene that you are modeling. Yeah, cool.
Is
not so cool.
jitter worth it with all the random calls?
Yeah, random. That's the question. I think that's a try and error because it depends on what you're doing, right? So how much accuracy are you aiming for? And you know, if you're looking for speed, then yeah, that's the question. You generally want to avoid any random call, right? Because it's just a waste of time.
I mean, I guess you can just have an array of pre-generated random variables. That won't be too.
That would be right. That would be an alternative. That's a good idea. Yes. Depends. Yeah, but it only works if you have a reasonably small scene, because otherwise you will probably see the non-randomness in your set of variables, right? So you need to have a large set of values available to make it appear kind of random, right? As opposed to, yeah, pseudo-random, which is anyway. But so then it probably would be more noticeable when you have weird artifacts again, I guess. I would imagine. So, but it's, yeah, but you're right, fundamentally, it's right. Anyway, so it's about color fundamentally. Here's another example. I found this on some website. It was quite, I think, quite illustrative about the different characteristics that we see. Here, the obvious most artifact producing one, but the cheapest one to calculate is the nearest one. For example, especially if you zoom in, you see quite noticeably that you have very harsh color differentiation and artifacts building based on this one. Here, the linear one is a bit works a bit better. And this one actually used the mid-match. So you have different sizes of textures. You're figuring out which projection is the closest to the one you're currently calculating, and then take the the nearest pixel from that closest texture, and use that to render the output. Yes, that's the idea. So you have those increasingly blurry smoothing effect here, and this very harsh discretized. Here you see the artifacts quite well as well in terms of the strides developing. So yeah, so that's the idea. It's just more computationally expensive, obviously. There have been some approaches to reduce the computational effort associated with this, because the idea of anisotropic filtering in the first place, or sampling in the first place, comes from the perception that we actually don't necessarily need to have the full resolution or a high resolution model in all directions, but actually could do it selectively as well. So if you have for example, if you apply it isotropically, it would imply into all directions, whether you actually see or not the model, you would apply the same calculations. So the challenge there is, does my player actually turn into that direction? If yes, well, it probably could possibly make sense. If the player doesn't, it's probably not worthwhile wasting time either representing the objects at all, and certainly not applying high quality rendering to it. So that's one possible way, but the alternative is simply to consider the angle when basically the camera perspective, when you're looking at a particular object, both in terms of direction as well as angle, and then based on that apply your filtering mechanisms. Either just, again, doing that approximation in one distance, or expanding the effort and actually having the complete texture wrapped out for the entire distance. So you actually have a texture that considers the distance representation as well. So even if you zoom out, you would still have a high quality rendering. In this case here, the example is taken from the, I think, flight simulator. So it's most obviously that it's probably useful to have a reasonably far view in this particular case, but in the first-person shooter, it's probably not super important to have an accurate distance representation. So, but here the idea that you have selectively high quality rendering and then increasingly blurry for left and right, or yeah, or the like. So yeah, that's the idea. So the idea is not only to use the filters, but use the filters with respect to the perspective that you are having as a viewer. So it's the whole magic there. In OpenGL, how do we do it? Again, we don't do anything, or nearly. Nearly anything. That's a bit of a pity here. Not sure how to do it right now, but so you said, and you saw it in the lab 4, I believe, the GLZ text parameter. So you need to set the filters that's applied for texture magnification, and then you decide, in this case, you use one of the algorithms of choice, GL nearest, linear, nearest mipmap, and linear mipmap linear. So you there's a set of different functions that you can actually apply. Hang on, I'll just bring up the reference page because that makes much more sense of the API, and you can play around with this and explore. Hang on. And complementary to the magnification is the minification, the what happens if we reduce textures in size. Hang on, where do I find it? So here you go. So that's all the possible algorithms used for the GL texture min filter. So if I reduce the size, what's happening? And those are the available ones here as well. So GL nearest, mipmap nearest, chooses mipmap that is most closely matches the size of the pixel being textures, and uses the nearest criterion. So meaning the texture element that's closest to the specified coordinates. So it doesn't really do an interpolation there. Again, the choice of the nearest pixel is fast, so performance, whereas quality is higher if you have a linear interpolation between the different coordinate colors. So yeah, anyway, so there's different options you can play through and explore, and yeah. But by default, nothing of that should challenge us really, unless we actually go serious 3D for now. But at that stage, you will need to make the call as to which ones you want to choose. For the magnification, we have the two ones as well, which is GL nearest, which is generally the fast one, and GL linear, which is generally a good one in terms of quality. So because it interpolates across all the candidates coordinates, texture coordinates, texture coordinates. All right. So that's just to highlight some of the challenges. Again, the URL is on the slide sheet there. You can just use this. If we go beyond the idea of textures, textures are not used only for colors. We use them only for colors for now, but they can be for other aspects as well. For example, for illumination. So based on your textures, so not so much based on your camera perspective and potential light in your scene, but based on your textures, you can also parameterize illumination of a given model. So you actually don't need an active light, but you just do it by textures, by indicating where a brightness of a particular coordinate. What else do we have? The other one was, an interesting one, which is, so we have normal mapping, bump mapping, and so on. I go through some of them just to get an idea. And the idea is that if we deal, that's probably a better one. So if we deal with textures, we can also, instead of just looking at color, you can also determine in how far your texture modifies the geometry of the object. So in texture, instead of using textures as a parameter to indicate the color position and so on, you actually change the geometry. So suddenly you have, for example, bumps in your object. So depending on where your texture maps, you suddenly could inject a bump into a sphere, right? Things like that. So you don't need to explicitly model that in your geometry. You can have a simple sphere, but only when you apply the bump texture, then you would see it. Or you have inject some noise, for example, as well. So you get this kind of more rich surface, for example, for if you model a planet and so on. So it would be another way of using textures. think about it like you probably have experience in OpenGL. In the end, OpenGL is quite flexible as to what you pass to your shader. What you do with it is pretty much up to you, right? Whether you actually use a particular input for rendering color, or for modifying the position, or for modifying the position of a particular coordinate and so on. It's pretty much up to you, right? So you do it in the shader. You just work under the convention that we have position coordinates, color coordinates, texture coordinates, and so on. But how you combine in the shader is ultimately up to you. And that's precisely where those ideas come in, because it's way cheaper to do that in the shader than to have it in your texture in the first place. So, because the more you can do on GPU, the cheaper. So what else do I want to do?
What's normal mapping?
Yes. That's right. Right. Okay. So the idea is to, if you have, yes, the idea is that you can smoothen or interpolate between of geometric shapes depending on the position to model certain elements that may not be explicit in your geometric representation. So the idea here, I like the idea of this line ridge on the car body. So if you have an otherwise rugged representation of this ridge on the car, you can basically smoothen it out by using the using a normal mapping textures on that particular coordinate. So it would just apply a again, a variation, it would modify the geometry so it's smoothened out, for example, where it's not the case in other places of the car.
So it's the opposite of tessellation, where you make something have...
The subdivision.
Yeah.
Tessellation is a subdivision of shapes. In a way...
I guess it has kind of the opposite effect, but it's not the same thing.
That's right. You have, yeah, good. I'm not sure. I need to think about this more. Wouldn't be able to suggest that. But the idea is there that you, instead of parameterizing color or anything else, again you indicate where on a particular where you modify the geometry, basically, as opposed to color or image or whatever else. Just say in this particular position. Smoothen the surface by applying a normal normalization across the geometry. That's
it's a selection
probably.
Tool.
Yes, a selection tool. So selective application.
Spaces, or you select areas of the model where the texel is being put, and you say that this area, which is marked by these texels, is going to be smoothened. And
that's
some
precisely.
algorithm takes action and does something.
That's right. So that's right. You can even do, obviously write the algorithm right in your shader itself, but in this case the texture would just signify which areas to modify. So it's similar to the bump mapping in a way, but here more selective in terms of areas.
Cool.
Cool. What else want to show? Yeah. Actually, you can also use. I think I have a good example here. Seriously? Not now. Well, go to your screen here, see if we find that, what I wanted to show. Good, internet works, that's quite handy. But an effect you can do as well is to use it to, this was the, where's the animation I want to show? There you go, like that one here quite a bit. So the idea is here, you can also, normal mapping, you can, in order to minimize your, the complexity of the minimizing number of polygons and the minimizing the complexity of geometry, another aspect is to basically copy geometric components here. So the idea is here using a normal mapping. Here is the idea that the left side here is modeled using the regular geometric primitives and those complex representation. But in this case, it's just a white plane. But you use this texturing mechanism to give the perception that apply the same effects basically to and based on an offset to this plane area and give the perception as if the same geometric elements would basically, or same model would basically exist on the plane as well. That's another application of the normal mapping that you could do. Yeah. So you basically copy elements from your scene and give them the appearance as if they are replicated in another position. Because you can again modify position based on that, but also consume any input that you get in your vertex shader, for example, and then project it elsewhere. That's a practical application of normal mapping, because it's very cheap. You don't waste time on your geometry, but you just waste time in the actual shader to do that mapping there. So that's yeah, it's a good, neat example of a visual effect. So yeah, apparently that's quite interesting, environmental mapping. So you're actually not so much looking at the mapping of a particular object, but you're just mapping the reflection of the object. So you're actually mapping what you see. You're mapping in the other direction, right? So it's kind of a real-time mapping of what the world looks like from the perspective of the object, and then map that onto the object. So it's a cheap way of doing reflection. That's one idea.
Yeah, it only works with static objects, though. If you move the object or rotate the object, it doesn't work. You'll have to change the texture if you move the object.
If you translate the object, right? If you rotate, probably get away with it, right? Oh no, that's right. That's right. That's right. Yes, yeah. That's right. Yes, yeah, I agree. You're right. Yeah, as soon as you do any transformation on the object and on the model, then you're kind of screwed here.
I mean, you can translate it a little bit, but
yeah,
can't get away with much. Cool.
3D pictures. What else is here worthwhile mentioning? Now we talked briefly about 3D textures. The idea is there. So here's the opposite. You have a volumetric representation, and you carve out what you need, throw away the rest, and that's your texture. And that you can map onto an object, or you can use it directly without any underlying object. Which has this hollow effect. If you do that, you probably know that from some games where you can navigate through the scene. You actually can move through walls and stuff like that, and has weird artifacts. And then there's the last concept, which is I'm not going into at all. It's like texture readback. The idea is that you use the output of the text buffer itself as a texture input. So you produce something using, in your frame buffer, the render to screen, but use that as input for further processing. So the interesting idea is that you can kind of do some sort of meta programming in the widest sense, that you basically re-injecting your output into your own processing and have some effects on that basis. So I don't know. So that's one of the ways you could deal with. Do some sort of GPU computation and have some, nearly evolving, if not evolutionary, effects on the output. So you move away from a pure graphics representation, because at that stage your texture could be anything that is some sort of data representation that is just uses a frame buffer for its output, right? So that's the concept of texture readback. We're not going into that. I think there was a course on GPU programming here, the third year-ish. And that would be a course that would be a candidate for those kind of.
Yeah, that's been removed, I think.
Oops. Yeah. Okay. Okay. So, but that would be another concept. Here's just about the idea. You can't. Textures are not only colors, right? Textures can be something else as well. So that's the idea to get across. But for our purpose right now, we're looking at textures. You need to consider the interpolation effect at zooming in, zooming out. But apart from that, there's no magic right now that we need to bear in mind. Perhaps we come back later. There's some other aspects, but those are the basic ideas. And effects of clipping, right? So if your texture is too small, too big for your window, or too small for your window rather, how do you deal with the borders? That's something you need to define as well in your code. And in fact, in your lab, you saw all those elements already, but hopefully you know what, you now have a better understanding what they mean in your code, and can play around with this and see what it does. Okay. Yes. So I'll see you in mobile, I guess.